Last time we talked about Cook's distance as we ended off our little section about recognizing outliers in the data set and potentially how they could influence the result of our model estimates. Okay, so that's why we titled that the section the effect of individual observation. So sometimes one or a few observations in our data set can actually cause our estimates of the parameters beta to change and have an outsized effect on those estimates. Okay, so last time we ended off by talking about one metric that we can evaluate to assess how influential points are. Okay, so we called this Cook's distance. Okay, and so just to remind you of that formula, we said that we call it d sub I. So the Cook's distance for the ith observation is defined as to estimate the regression model parameters without the observation. So that's beta hat with an I here. Okay, and then compare it to the regression estimates with all the data. So that's beta, that's the usual least squares estimate for beta hat here. Okay, and so Cook's distance is a way to measure how different the betas are between these two ways of fitting the model. Okay, and then there's some stuff that some terms that provide some sort of a standardization. So this is, we put the X transpose X matrix in the middle, and so we have here beta hat I minus beta hat, and I think I missed a transpose here. Okay, and then on the bottom we have sigma hat squared times the number of predictors. Okay, so that's the definition of Cook's distance. Now, last time I showed you how we can take the X transpose and put it in here, and the X is put in this term, and then essentially what this gives us, it gives us a scaled Euclidean distance between the fitted values of the two models. Okay, so let's look at this in a little more detail today. And so this is going to be quite a bit of linear algebra, but I assure you this is the last time we're going to do such a long linear algebra. So you have some of that to do on your last assignment, and so I will do my fair share and show you the linear algebra proof of how we get from this expression to the expression for Cook's distance that involves the studentized residuals and the leverage. Okay, so let's work on this expression together. Okay, so first let's define a bit of notation. So for the ith observation, okay, so it's going to have its predictors, the values of its predictors. Okay, so they're going to be xi1, xi2. So I'm going to write it in the vector form, xi1, xi2 up to xip. Okay, and then I'm going to just for notation's sake, I'm going to define. So I'm going to call this thing a vector. I'm going to call it. So let's put this into a row. So this is in row form. So let's transpose it. So we get a usual column vector, and then call that. Let's call that bi. Okay, so let's define that notation. So I'm using v as opposed to x vector because usually when we say x vector, we're talking about the columns of x corresponding to the predictor. So I just use the notation v to stand for all the available predictors, x1 up to xp for the ith observation. Okay, and so so that means then we can, so the matrix X then can be written as, so in other words, it's composed of these rows, so B1 transpose V2 transpose, and so on up to Vn transpose. Okay, so this is the matrix X would then be obtained by taking the row form of this and then stacking them all together. Okay, and so our matrix X transpose X. Okay, so then we do the multiplication in terms of these vectors V. It would look like this. So if I transpose it, I would now have V1 in the column, and then up to Vn. Okay, so that's X transpose in terms of these predictor vectors I've defined, and then times the X matrix. So V1 transpose up to Vn transpose. Okay, and so I can multiply this in vector form. So I have V1 transpose, and then add each of the contributions from each of the Vi times Vi transpose. So this looks like the sum from 1 to n. Okay, so we have Vj transpose. Okay, so that's X transpose X in terms of vectors that we defined. There's a question: Are we missing the constant term? Yes, of course. So let me fix that. Thank you. Yeah, so that is thanks for that note. Of course, we mean here the ith row of the X matrix, and of course the first column. Since we usually have intercepts, we'll put the value 1 there. Thank you. Okay, so this all follows. Okay, so each row is Vi, and then transpose, and then we have that expression as in terms of X transpose X matrix in terms of the vectors V. Okay. All right. So we have that, and so now let's also look at the hat matrix then. Okay. So recall the hat matrix is defined as X transpose X inverse X transpose, and then X over here. Okay, so that's the hat matrix. So if I want to get the so the leverage, if we recall, is the ith diagonal element of H, and so there's another question: what happens to the I not equal to j terms? I am looking at the entire X matrix right now. So this has all the observations. So I haven't deleted it yet. So this all follows in terms of using the full X matrix. So I'm just laying some of the groundwork here. So H is the hat matrix. So the ith diagonal element. So how do we obtain that? Well, we need. So in terms of this, we can. So we need to take the ith row of this X and then multiply with the ith column of the second matrix. Okay, so we can express it as in terms of these vectors. So I need to take the ith row. So this would be V I transpose, and then I will need the ith column of this whole thing. Okay, so how do I get that? So I'll need to take X transpose X inverse, and then I want the ith column, so I'm going to use the corresponding column of X transpose, which is Vi. Okay, so that's the leverage. So remember, these are the leverages. Okay, so that was defined last time. So remember, the leverage tells us conceptually whether the so observations that have high leverage tend to have explanatory variables with values that are far away from the rest of the points. So they tend to be outliers. High leverage points will tend to be outliers in the x dimension. Okay, so that's useful. So keep this fact in mind because I'm going to use this property quite a lot today to simplify some of our expressions. Okay, so that's how we can write the leverage for the ith observation in terms of these vectors in the X matrix. Okay, so now let's actually move on to looking at what happens when we delete. Because in order to calculate Cook's distance, we need to delete the ith observation. Okay, so let's say now let's let xi be x with the ith observation deleted. And similarly, okay, let's call y vector I be the response vector with ith response deleted. Okay, so with that defined, then we can do some of the equivalent calculations. So if I now do x, then okay, xi. So if I do this same calculation now, but with the x vector without the ith observation, so xi transpose times xi. Well, what's happening is I'm gonna take out one column here and take out one row here. So what we get is the exact same sum, but with the ith thing in this sum removed. Okay, so it will just have the same form. So j not equal to I. Okay, since we have omitted the ith elements in this multiplication, and otherwise it looks the same. So bj transpose. Okay. And so we see that we can actually compute the difference between these two matrices. And so x transpose x can be written in terms of this guy plus the term that is missing. So we have x I transpose x I, and then plus, well, which one was left out? Well, is the ith term. So we can add that back. Vi transpose. Okay, so that's the first relationship we need. Okay, and so in similar way, we can also do the corresponding thing for the y vector. Okay, so similarly. Okay, so x transpose times the vector y. Okay, so it's almost the same thing, except now you have the values, scalars, y1 up to yn, in this form. So it'll be summation from 1 to n vj y j. Okay, and then similarly, I can do the same thing, but with again with the form with the ith observation deleted. So that gives me x I transpose y I. So again, j not equal to I, vj yj. And then again, we can see that we can relate the two by simply adding back the ith term. So x transpose y can be written in terms of the one with the ith observation deleted plus the term that was omitted, which is vi yi. Okay, so far we have these two preliminary relationships that would be helpful. So I'll just box them because these are the ones we're going to use subsequently. So we can express the usual things that we use, x transpose x, and also x transpose y in terms of the forms of the matrices with the ith observation deleted, and so now we can relate the two for the purpose. So as you can see, we're working towards being able to calculate beta hat I in terms of these quantities, and that will get us on our way to simplifying these. Okay, so these are the three things I will need to use from what I've written so far. Okay, so now let's proceed. Okay, so the next step is to write out what beta hat I is. So since we're doing least squares, we know how to express beta hat I directly in terms of the things we defined, because beta hat I simply uses xi and the matrix xi and the vector yi, so with the ith observation removed, and then we do least squares on that. Okay, and so we now fit least squares using x without the ith observation and y without the ith observation to obtain to obtain beta hat I. Okay, so we know how to do it. If you give us an X matrix and corresponding response vector, so now these have n-1 observations. Okay, so we use the usual least squares formula on that. So we have xi transpose xi. So we take inverse, and then xi transpose y with the ith removed. So that's the same form, except we now use these expressions that have n-1 observations. Okay, so now let's simplify this. So now you see why we've computed these expressions, because now we can express both of these terms in terms of the original X matrix and the original Y vector. Okay, so let's make those substitutions. Okay, so this thing, xi transpose xi, I've used this expression, so it's going to be x transpose x minus vi transpose inverse, and then substitute the same thing for this guy using the second expression. So we have x transpose y minus vi yi. Okay, now we gotta take the inverse of this thing. So we need to look in our cookbook for matrix algebra. Well, how do I take the inverse of an arbitrary matrix minus invertible, assuming x transpose x is invertible, which is in our context, and then we need a vector times vector transpose. So we need to look up this fact. Okay, so here we need to use the fact. So I have matrix A, which is invertible, and then minus of this vector product. So this inverse looks like this. You have A inverse plus A inverse, and then this vector product, and then another A inverse, and then 1 minus A transpose matrix A, and then vector A.
okay, where A is n by n is invertible. I'm sorry, A is should be more general, so A is square and invertible. And of course, the dimensions where and dimensions match. Okay, so we're going to use that to simplify the first term here. Okay, I'm trying to leave up this back. We'll use that one shortly. Okay, and so let's apply that here. So we get the inverse of the first guy, so x inverse, and then use this formula. So we have x transpose x inverse bi transpose another x transpose x inverse, and then on bottom it's going to be 1 minus bi transpose x inverse and bi. Okay, and then all that times the x transpose y term. Okay, so that's the simplification. Missing on the bottom right result. So this guy, vi would need to be transposed. So question. Oh, I see. So this is missing. The x is missing the transpose. Yes. And then I missed an I on this one. This is what happened. Wait, this is right. Okay. Yeah. So this one has a, and then did I write it correctly here? So this term and the bottom term match up. So this is xi transpose yi and then xi transpose yi. Yes. Thank you. All right. So we have looks like we have quite a bit of handful of stuff here, but this is where this identity comes into play. So actually, this is where the leverage actually shows up here in the denominator. So this is going to be HII. Okay, so there's another question. When we are we adding that row, or are we adding that value to the vector? I'm not sure which expression that is asking about, but I will try to answer that if you could tell me which expression you're asking about. But in the meantime, let me just point out here. Then this is where we use the leverage. So this is H. I'm going to substitute that in. Okay, so let us start simplifying this. Okay, in the meantime. Okay, so we have basically we're going to have 4 terms. Okay, so the first, so we have something plus. We have like a plus b, and then we have like c minus d here. So we're going to multiply everything out using rules of matrix algebra. So our first one is simply x transpose x inverse, x transpose y. So the question is referring to the x transpose y vector expression. Yeah, so this would be a matrix.
sorry, this would be a vector. This would be a vector subtraction. So that is the operation that we are that we are doing here. Each of these guys would be of dimension. So this guy would be p plus 1. So this is a vector subtraction here. Okay, so we have this term, and then we have next term, which is minus x inverse bi yi. Okay, and then we have these two terms. Okay, so let's write them out. Both of them have a 1 minus hii on the bottom. Okay, so plus 1 minus leverage. Okay, and so I'm going to get a little bit long. So I'm done using these. So I'm going to do my stuff in the room. Okay, so we have on the top bi transpose. Okay, so we have this. X transpose y. And then the last term is it's this one, so minus okay. So now those are the 4 terms. Okay, let's delineate what's here. So this is what we have, and so it's a bit of algebra. So let me just pause here for a moment, and it's also a good time to pause and show you what's under here. So this is a poppy, and as you probably know, so today is Remembrance Day, which is marked in the Commonwealth countries as a way to commemorate the soldiers who fought in the wars. And so why the poppy? Well, because as a mark of remembrance, well, because John McCrae wrote the famous poem, which is called "In Flanders Fields." So that's why we have the poppy, and so that's a little artistic rendition of that. Okay, let's continue with the simplification here. So first thing we notice is that this term is actually just beta hat. That's by definition, and likewise we also see a beta hat down here. So we can make those substitutions. And we also see that there's a substitution here, which is the leverage. Again, we see the leverage show up in this term here. Okay, so that will help simplify things quite nicely. Okay, so we have, all right, so we're gonna finally use that at the end and substitute everything. So right now we have beta hat. So I'm going to substitute beta hat in here as well, and in here, and then I notice I have x transpose x inverse of vi. Okay, and you notice it appears on all of these terms. So I'm going to factor it out. So I'm going to pull out x transpose x inverse vi. Okay, so what do we have inside? We have a yi. Okay, so we have yi, and then we're going to substitute beta hat in here. So we have minus. Okay, so this is minus, so we're going to put minus vi. Transpose and then beta hat. Okay, so make that substitution. This will be over the denominator, 1 minus hii. And then on here we have minus, what's left here is hii times 1yi. Okay, so we got most of it. So this minus is on the whole. So minus, and then vi. So you have yi. And yeah. Okay, that's correct. Okay, so. What we need, okay, so this looks a little weird, yi is outside, so naturally the next thing to do is simplify this, so this becomes put yi with the same denominator, so it's yi minus hii yi, and then that's going to cancel with this hii yi over here. Okay, so we're going to do that next. Okay, so beta hat, so x inverse vi. Okay, and so what's left here is, so we put with a common denominator, and what's on top, yi times this, so that's going to cancel that, so we have yi minus vi transpose beta hat. Okay, now this is getting, we're getting there, so what is this, now what is this thing? Yi minus, okay, remember these are the predictors associated with observation yi, so this is taking beta 0 hat plus beta 1 hat times xi1 and so on. So this is this thing is the fitted value. So this is mu hat I. So this is taking yi minus its fitted value. So this thing in red here is the residual. Okay, so with that in mind, we now have a relationship between beta hat I and beta hat. Okay, so in particular, what we have found now is that, so to summarize this, okay, so to summarize what we have so far, that means beta hat without the using the ith observation omitted in fitting minus the beta hat that uses all the data is this difference here. So this part is just a scalar. Okay, so we have ei over 1 minus the leverage, and then we have minus signs, and then x transpose x inverse vi. Okay, so that's the expression that we can now use in the calculation of Cook's distance. Other thing to note here is that, okay, so it looks like when we say beta hat I, it looks like we actually, so at first glance, it would look like we need to do a separate calculation. So we need to fit another regression model in order to calculate what beta hat without the ith observation would be. So what this expression tells us is, in fact, we don't need to fit a separate regression. We can actually compute what beta hat I would be simply on the basis of quantities associated with our model fit using all the data. In particular, I can calculate it by simply taking the difference, beta hat, okay, and then all this stuff, EI is from the full regression, HII is from the full regression, and then all this stuff I already have. So in fact, we can get beta hat I from the regression with all n observations. In particular, don't need to fit a separate regression. Okay, so beta hat I can be calculated from quantities that involve the regression with all the observations. Okay, so that's a key point here, which is why Cook's distance is then pretty really quick to calculate. Now we see we don't actually need to fit we don't need to fit another regression. We can simply get these guys by adjusting. So this, you can think of the regression without the ith observation as taking the estimates from all the observations, and then with this adjustment factor, okay, EI minus 1 over HII on this part. Okay, so that helps us conceptualize how to actually get Cook's distance in practice. Okay, so our last step is simply to plug everything in and simplify this expression. Okay, so let's do that. So I'm going to use this expression now and work from here. Okay, so let's plug this in. Okay, so we have on the top, we have the constant minus EI, 1 minus HII. And then we're taking the transpose of this thing, so we can transpose this. So we have BI transpose X inverse. Okay, this guy is symmetric, so we don't need to do anything here. Okay, and then in the middle we have X transpose X, and then on the other side we have another of these terms. Okay, and so that's all the stuff we have on the top. Bottom is sigma squared p plus 1. Okay, so now I've used this fact. So now we just need to simplify the expression on top. These guys are just scalars, so I just pull them. I can just pull them out. So we have the square of the residual, and then on the bottom, I have a sigma squared. I have 1 minus HII. Okay, and then I will have, so I have two 1 minus HIIs. I'll write one of them here, and then I'll write the other one over here, 1 minus HII. Okay, and let's simplify what we have up here. Okay, so we notice one of these guys cancels, X transpose X inverse, that's gone. And what's left here is VI transpose X transpose X inverse VI. Okay, and so we recognize that
again, we have the hat matrix, where this refers to the ith diagonal element of the hat matrix. Okay, so I'm going to combine this stuff together. So this stuff is what's left in red, which simplifies to get another copy of HII, and then on the bottom we have P plus 1. So we're basically there. We just need now to recognize what is this part here in red. Okay, so this is where we remind ourselves of what we learned about studentized residuals. So remember, let's do it here. So the studentized residual is DI, which is to take EI and then divide by sigma hat 1 minus root of 1 minus HII. So this is in fact the square of the studentized residual. Okay, so we are done. So once we make that substitution, we have DI squared, and then we have HII over 1 minus HII, and then we have 1 over P plus 1. Okay, and so that matches the expression that I claimed last time. So this is the equivalent way to calculate the Cook's distance in terms of the studentized residual and the leverages. Okay, as claimed. So we can calculate Cook's distance in terms of studentized residual. In fact, all we need is the absolute value of it because we're going to square it. Okay, so this, remember, the absolute value DI measures how far away in the y direction, so in terms of the response variable, how far away the fitted response is. Okay, so this absolute value, remember when absolute value DI is high, that gives us some indication that we could have an outlier in terms of having an extreme value of the response variable. Okay, so it involves absolute DI and also the leverage. And then leverage, as we recall, gives us high leverages give us indication that that the ith observation could have extreme values in terms of the explanatory variables. So Cook's distance combine these two, and so to summarize, well, what are the points that are most influential in the regression? I alluded to this at the end of last time. So observations, the most influential observations on, and remember when we talk about influence, we're talking about on the regression estimates. So the estimates beta are those with high DI and also leverage. Okay, so that's the derivation that we left last time. So now we have filled that in. Okay, so for the rest of today, I just want to show you some examples to do a demo in R. So I'm going to revisit our one of our data sets and look at these measures. So we're going to look at the studentized residuals, we're going to look at the leverages, and we're also going to look at Cook's distance. Okay, so I'll be right back with you on the computer. Okay, so I guess RStudio doesn't really like me. I have to restart that. Just give me a second here. Okay, so let's look at some of these three ideas. So we're gonna look at studentized residuals and leverage and Cook's distance. So let's load up our Python data sets. Okay, so I'm gonna rerun the things I did when we looked at model assumptions and box-Cox transformation. So I'm gonna rerun that code. So the first few lines are the same as what we did in our last demo with this data set. Okay, so we're going to define the variables, fit the initial model, and then we observed that time that the regression assumptions weren't very well satisfied. And so, for example, we could address most of those issues with a transformation in that case. So I ran a transformation, used a lambda of, so we transformed y to the power 0.384, and then we fitted a new model using the transformed response. And then we had these residuals, and we had the normal Cucu Plot, which showed still some deviations in the tails, but not as bad as the original. So for the sake of illustration, I'm going to use this fitted model to demonstrate these various quantities. Okay, so first is how to calculate them, and that's actually quite straightforward. There's built-in R functions that calculate all three of the things we discussed. The studentized residuals is calculated like this. So R will just return a vector, 1 for each observation, corresponding to the studentized residual numbered by the index. So for the 248 pythons in this data set. And similar thing for leverage, so that's extracted using the function hat values, and similarly for Cook's distance. So each of them will compute the vector, 1 per observation. So all we need to do in there is just put in the fitted model, and these will be computed. As we learned today, all these can be computed purely on the basis of the fitted model. We don't need to refit any models, for instance, to calculate Cook's distance. Okay, so here are all the numbers. So it's helpful to again visualize them with plots. So let's work through the different plots. Okay, so our usual residual plot would take the fitted values and the usual residuals, but I think we mentioned when we were talking about residuals, you could also do a similar plots with the studentized versions, even though it's more common to use just the raw residuals themselves. But we can also do a corresponding plot with having standardized for the different variances. Okay, so that's this plot, especially for relatively larger samples. You notice these don't look all that different, so there's only slight changes because of after adjusting for the square root of 1 minus the leverage. Okay, so most points aren't going to change. So what points are going to actually shift a little bit are the ones with the high leverages. Okay, so high leverages are going to have a high value of HII, so 1 minus HI will be small, and so it's going to take those points and it's going to adjust them upwards. Okay, so high leverage points will change, but most points which are not don't have high leverage will look fairly similar as to our usual residual plot. Okay, and so as a rule of thumb, we can use about 3
standard deviation. So remember, after doing this standardization, the variance is approximately 1. So the vast majority of our data should lie within 3 standard deviations of 0. So just put in lines that marked -3 and +3. Well, nothing really goes up to +3, but we do see there's a couple points that have quite a large negative residual. So which ones are they? Well, we can use the which command to figure out which index they are. So basically, I'm just taking the absolute value of the studentized residuals from the model and asking which of them have absolute value of di greater than 3. So that tells me there are 3 of these observations, and so we can take a closer look at them. For instance, if I want to see which one that was, so I could 122, and you can actually look at the actual the variables associated with the 122nd observation, for instance. Okay, similarly, we can do our Cucu plots. Not surprisingly, they don't look all that different because it's really only a few points with high leverages where the studentized residuals are actually going to be a little bit different than the original ones. Okay, so next let's look at leverage plots. So we can plot the leverages as a function of the index in the observation. So this will just plot all the hat values that we could extract using the command we saw earlier for getting all the values of the leverages. So let's just put them all on the plot so that they're easier to visualize. Okay, and so we notice here that most of the leverages are close to 0. So HII is generally quite small, as we've said is usually the case in practice. And there's a few that are a bit larger. So it turns out here that the observations in our data sets are mostly ordered by the size of the Python. I think that was just the way the data set was sorted. So it just happens that the smaller Pythons were at the beginning of the data set, and then the largest Pythons were at the end of the data set. Just I think that was the way the data curators sorted the observations. So that's why you see this bit of a pattern here. Okay, so we'll see that in just a moment. But for now, let's use our rule of thumb and look at what we consider high leverage points. So generally, I mean, it's been recommended to look at those that are more than twice the average leverage. So let's put that line onto our plot. So we take 2 times the mean of the leverage, so 2 times the mean of all the hat values, and let's add that line onto our plot. Okay, so it's pretty low. It's down here. So the points that relatively have higher leverage are the ones with the low indexes, and then the ones with the high indices. Okay, so which ones are they? So let's find which indices. So they're the ones, the early part of the data set and the late part of the data set. And the only reason for that is because the data curator in this case seemed to have sorted by the size of the Python. So we extract those rows. It turns out, well, these are indeed the smallest Pythons, the lowest masses, and then the really big Pythons. Okay, so thinking of that conceptually, then, well, why do these have the highest leverages? Well, these are, turns out, well, the values of the explanatory variables, well, the continuous ones are SVL and mass. Okay, and so these, of course, for the really small Python and the really large Python, these values of the predictors are going to be the furthest away from the other points. Okay, and so if the values of x are going to be far away from the rest, then those are going to be the ones with the highest leverages. Okay, so just because of the way the data was sorted here, we see the highest leverage points to be the really small ones, and the small snakes, and the really large ones. Okay, So finally, we have Cook's distance. So again, let's just first plot all of them. Okay, so most of the Cook's distances are close to 0, and then we have some really a few larger ones. There's again various rules of thumb for how to consider Cook's distance to be large. So here I've just used a value of 0.5. So I'm going to add a line here for 0.5. So there's just one point that has a Cook's distance larger than 0.5. So which one is it? Well, it is 240. It's 248. Okay, and so remember that as we mentioned, Cook's distance combines studentized residuals and leverage. So both of them play an important role in determining which are the most influential points. So the most influential points tend to be outliers in both the explanatory variables, one or more of them, and also in terms of the response. Okay, so it turns out the most influential point, according to that criteria, is the last observation, so 248. So notice, okay, so which were the outliers, or which had the largest studentized residuals were these three observations, and then the ones with the highest leverages were these ones. Okay, so notice that the one with the highest Cook's distance is not among the three with the highest residuals, but it is among the more high leverage points. So overall, after combining both the residuals and the leverages, it turns out 248 is the most influential on the regression estimates. Okay, so let's actually look at let's also look at the effect in terms of the data. So, okay, so first we can extract, so here's again the summary of the regression, and so we can extract the coefficients, so the beta hat, by taking the coefficients from the fitted model. Okay, so that's these values, about -8 for an intercept, -1.78, and then the corresponding estimates for mass and the snout event length. Okay, so these are the beta hats with all of the data. Okay, so let's look at the actual effect in terms of like removing a couple of observations. So, for example, let's remove the actual observation 248. Of course, remember we said we can actually calculate beta hat without having to refit, but just for simplicity, let's just do that. So to demonstrate how we can actually do so manually. So I'm just going to remove here minus 248. So I'm taking out the 248th row from the data set, and I'm going to fit a new regression model. Okay, so that shows you how we can do that manually, and we can extract the coefficients. So notice what we want to pay attention to here is how the estimates actually change on the basis of just one data point. So we've only removed one observation, but we see here that these beta hats actually have changed quite a bit, considering we only removed one observation out of a data set with 248 observations. Okay, so notice in particular we care the most about these three regression coefficients. Notice this went the beta hat for the gender of the snake went from -1.78 to -1.66, which is somewhere between a 5 to 10% change, and it's only one observation. So just taking out one observation out of 248, that's less than half a percent of the observations, actually has a pretty big effect on the regression estimate. Similarly for mass, so you notice it went from so here you have 3 zeros and you have 446, and then went up to 574. Okay, so this is a very more than a 20 to 30% change in the estimate of this coefficient with just one point removed. And then also we see about another 10% change to the beta for SPL. Okay, so that's what we mean by an influential point. when it's removed from regression, so having the 248th observation in the regression, forfeiting the regression versus not, actually has a pretty large impact on the beta hats that come out of fitting the model. Okay, so that shows more concretely what influential points do to the regression. Okay, and just to compare, finally, let's try just throwing out just some other observation. Okay, so here, just to illustrate, I'm just going to throw out the 50th observation. So you notice it's not very influential. It's one of those points in this part of the plot. So influence is pretty low. So what happens when we throw out some other observation? Let's say the 50th. Okay, so I'm going to fit the model without, say, the 50th observation. So let's do that and look at the coefficients. Okay, so we notice in contrast, when we throw out a non-influential point, so in this case the 50th one, you notice these regression coefficients don't change all that much. So minus 1.785. So the first 3 digits here are exactly the same. It's just not until you get to minus 1.7805 that we start to see differences between the estimates. And similarly for mass here, we also have 0.446 all matches until we get to the 4th digit. And likewise SVL here, 1.1431, again all matches. So you notice the beta hats don't change very much when we throw out one observation that has a fairly low influence. Okay, so that helps us see, and that indeed the most influential point here does have an outsized impact on the regression coefficients for our fitted model. Okay, so that's what I wanted to show you in terms of illustrating the idea that some observations can be more influential on our regression estimates than others. So I think I mentioned also when I was talking about outliers that we generally don't want to arbitrarily start throwing things away from the regression unless we have a good justification for why they don't belong in the data set. But these metrics do help us see which observations in our data set, assuming there are no errors in data collection and they're a valid part of the sample, how individual observations affect our regression estimates. Okay, so that's what I wanted to cover today. So I'll just pause for a few moments to see if there are any questions before we end today. Okay, so let's call it a day. We will be back on Monday. We're going to talk about cross-validation schemes and in particular how to use a different metric for assessing model performance. So we're going to look at things like prediction error for model training. So we're going to shift gears and do some of these sorts of predictive analytics next time.